Kruskal's algorithm for computing the minimum spanning tree of a graph. Now let's start off with some basic definitions. What is a spanning tree? A spanning tree is a subgraph that has the same vertex set as the original graph, and it is also a tree, which means that it must be connected and must not contain any cycles. A graph may have a large number of spanning trees, but not all of them are minimum. A minimum spanning tree is the one in which the sum of weight of edges is minimum. Now, let's look at the steps for finding the minimum spanning tree using Kruskal's algorithm. The steps are fairly simple. The first one says, sort all the edges in non-decreasing order of their weight. Now, this is a greedy algorithm. So what it does is that it picks the smallest weighted edge not in the spanning tree and checks if adding this edge to our spanning tree obtained so far forms a cycle or not. If not, then this edge will be a part of our minimum spanning tree. If it forms a cycle, we simply discard it. We need to keep repeating this step for all edges in G until there are exactly v minus 1 edges in our minimum spanning tree, where v is the number of vertices in G. Now let's try and understand these steps with an example. Consider the given graph which has 9 vertices v0 to v8. The number on the edges represent the weight of that edge. We need to obtain the minimum spanning tree of the given graph. The first step says sort all the edges in non-decreasing order of their weight. Let's do that. You can see that all the edges are written in the sorted order by their weights. V7, V6 being the smallest weighted edge with weight 1 and V3, V5 being the maximum weighted edge with weight 14. Now let's move on to step 2. Pick the smallest edge V7, V6. Being the first edge, obviously it does not form any cycle. So this edge will definitely be a part of the minimum spanning tree. The edges represented by the yellow lines here are the ones that are part of the MST. Let's pick the next edge V8, V2. Again, it doesn't form any cycle, so it will be added to the MST. Next is V6, V5. Again no cycle being formed, added to the MST. Now pick V0, V1. Check for cycles, no cycle formed, add this edge to the MST too. Next is V2, V5. Again, adding this edge to the MST doesn't form any cycle. This edge will also be a part of the MST. Now, let's look at V8, V6. If we add this edge to the MST, it forms this cycle, as you can see here. So, this edge won't be a part of the MST. Now, adding V2, V3 to the MST doesn't lead to the formation of any cycles. So, V2, V3 will also be an edge in the MST. Now, V7, V8 can't be a part of the MST because adding this edge would form this big cycle. This one. Adding V0, V7 to the MST doesn't form any cycle. So it will be added to the minimum spanning tree too. Also, note that we are keeping a track of the number of edges in MST. Because according to the third step, we need to stop as soon as we have V minus 1 edges, which is 8 in this case. Now, let's try and add V1, V2. Note that a cycle is being formed here. So V1, V2 won't be in the MST2. Next is V3, V4. Adding V3, V4 doesn't form any cycle. So add this edge to the MST. Note that we have now 8 edges in our minimum spanning tree. So we have reached the terminating condition. Thus, we have successfully obtained the minimum spanning tree of the given graph. We can also calculate the weight of this minimum spanning tree by adding the weight of the individual edges in this tree. We see that they add up to 37. Time to look at the pseudocode for this algorithm. Line 1 initializes A to an empty set. Line 2 and 3 create V trees, each containing one vertex. Line 4 simply sorts all edges in the original graph by non-decreasing order of their weights. In lines 5 to 8, we one by one pick edges in the order of their weight, lowest to highest. The loop checks for each edge UV whether the endpoints U and V belong to the same tree. If they do, adding them to the MST would form a cycle, so they will be discarded. But if not, line 7 adds edge UV to the MST. Line 8 merges the two trees using U and V. Finally, return the set A containing all the edges belonging to the minimum spanning tree. Now let's try and analyze the complexity of Kruskal's algorithm for minimum spanning trees. Initializing A to an empty set takes constant time. The make set operation in lines 2 to 3 grows very slowly. Sorting E edges takes big O of E log E time. Lines 5 to 8 perform the find set and union operation for each edge in G, thus taking a time of big O of E log V. So overall complexity of Kruskal's algorithm is big O of E log E plus E log V. But value of E can be at most big O of V square. So big O of log V and big O of log E are the same in this case. Therefore, overall time complexity is big O of E log E or big O of E log V. Thank you for watching the video. Please leave us your comments.